Good morning, everyone. So today is week 11 of our NPTEL course, Introduction to Algebraic Geometry and Commutative Algebra. So, our syllabus today is prime spectrum and Zariski topology. Uh, so let us start discussing the problems. Uh, so okay. So let us start with the first problem. Let Y be a closed subset. That means it is a set which contains all the prime ideals containing an ideal, so that the points are dense in Y. So yeah, we have to first prove this. So let Y be is a closed collection of all prime ideals containing some ideal I, that is Vi. To show that the closed points are dense in Y, it is enough to prove that every non-empty open subset of Y contains a closed point. Now let U be a non-empty subset, open subset of Y, and since the closed sets of Y are of the form Vj intersection Y, and the basic open subsets are forming a basis, we may write that U equals to Y intersection df for some f of capital A, where df equals to all the prime ideals such that f does not belong to that prime ideal. And because U is non-empty, the localized quotient B equals to A mod I localized at F is non-zero. And how is this happening? Since if U was empty, then it would be equivalent to saying that F lying in every prime ideal of A mod I, and that means that F belonging to the nil radical of A mod I, which would force A mod I F to be 0. Now A is finite type over K, hence so we know that A mod I is finite type over K, and therefore its localization is it is also finite over K, and since B is non-zero, it has a maximal ideal n, and let M be the inverse image of n in A mod I, then M is a maximal ideal of A mod I, and so it corresponds to a closed point of Y. Moreover, because uh, uh, because it was localized at F, and the ideal M does not contain the image of F, hence the corresponding point lies in df intersection Y, which is U. Thus every non-empty open subset of Y, which we took U, contains a closed point, and therefore the closed points are dense in Y. Now you should try the that question B, that so that spec A is finite if and only if A is finite K algebra, that is dimension of A over K is less than infinity. Now let us solve this. We prove the two implications separately. So first one, we consider A as finite dimensional K algebra over K algebra. Then we have to show that spec A is finite, that there are only finitely many prime ideals. Now if dimension of A over K uh, is finite, then A is an Artinian ring, and this is because every descending chain of ideals is a descending chain of K subspaces, hence stabilizes. And in an Artinian commutative ring, every prime ideal is maximal, and the ring decomposes as a finite product of Artinian local rings. And in particular, there are only finitely many prime ideals. Hence, spec A is finite. Now, if spec A is finite, then A is finite dimensional over K. We have to prove this. Since A is of finite type over a field, it is Noetherian. Hence, it has only finitely many minimal prime ideals, say P1 up to PR. And let R be the nil radical of A. Then the reduced part of A red, is A mod R, injects into the product A mod Pi, where I runs from 1 to R, and A red is reduced and its minimal primes are precisely P1 mod R. Now spec A is assumed finite, so each closed subset Vpi is isomorphic to spec of A mod Pi is finite as well. Each ring A mod Pi is a finitely generated integral domain K over K with finite spectrum. We claim that each such domain is finite dimensional over K. And so let B be a finitely generated integral domain over K with finite spectrum. By Noether normalization, there exist algebraically independent elements x1 to xd of B such that B is integral over polynomial ring K of x1 to xd, where D equals to transcendental degree of fraction of B, fraction ring of B, fraction field of B over K. And if D greater than 0, then K of x1 comma xd has infinitely many prime ideals, hence infinitely many maximal ideals. For example, KT already has infinitely many maximal ideals, and there is a surjection kx1 to xd to kx1. So spec kx1 to xd is infinite, and since the extension kx1 to xd is contained in B is integral, the induced upon spectra is surjective. Therefore, spec B would be infinite, contradicting the assumption. Hence, D equals to 0. Thus, B is algebraic over K, and since B is finitely generated as K algebra, it is generated by finitely many algebraic elements, and therefore it is a finite dimensional K vector space. So each K API is finite dimensional over K, and A reduced is contained in the product of A mod Pi, shows that A reduced is finite dimensional over K, and finally the nil radical R is nilpotent because A is Noetherian, and choose n such that R to the power n is 0, and therefore A has the finite filtration, and we have this, that A is contained in R square and R to the power n 0, and each quotient R to the power j mod R to the power j plus 1 is finitely generated module over A mod R, which is A reduced. And since A reduced is finite dimensional over K, and each of these quotients is finite dimensional as a K vector space, therefore A being built from finitely many finite dimensional successive quotients is itself finite dimensional over K. So therefore our proof is complete. So what we conclude is that spec A is finite if and only it is a finite dimensional as K algebra. So let us try the next problem. You can read it here, and after that we will discuss this. So let us start solving this. The question says that let xy be indeterminate over C, and let A be a ring which is C of xy, and B is C of xyt mod xt minus y, and let pi equals to I square, which is a map from C of spec B to C of spec A, which is C square, and be the map associated to the inclusion A of B from A to B on the C spectrum. So what you are seeing is that spec A is called the affine plane, and B is some affine space, and since there is a map from A to B, or you can say inclusion, so there is a map from spec B to spec A, and we have to show that pi induces a homeomorphism from pi inverse dx to dx, hence an open immersion from pi inverse dx to C2, and further prove that the fiber pi inverse 0 0 is homeomorphic to C, and check that image of pi is dx union 0 0. Now we identify the spec A with C2, and spec B with the affine surface B of xt minus y from C3, and under this identification the map pi is simply the projection pi xyt equals to x comma y, and restricted to hypersurface xt equals to y. Now the restriction over dx is an isomorphism. How do we prove that? Now recall that dx equals to all those two tuples x comma y such that x not equals to 0, and on the open set dx the equation xt minus y equals to 0 can be solved uniquely for t equals to y mod x, and this is the key point. Algebraically, after localizing at x, the relation xt minus y equals to 0 gives t equals to y mod x, y bar by x in bx, and hence bx equals to c of xyt localized at x mod xt minus y, which is isomorphic to c of x in x inverse comma y, which is isomorphic to ax, and therefore the induced morphism on the corresponding open sets is an isomorphism. And concretely on points, the inverse map is dx going to pi inverse dx, which is taking x comma y to x comma y mod x, and this is well defined because x not equals to 0 on dx, and it is clearly inverse to the projection x comma y comma t going to x comma y, hence pi inverse dx is going to dx is a homeomorphism, and since dx belongs to C2 is open, this shows that pi restricts to an isomorphism onto an open subset, and therefore pi gives an open immersion on pi inverse of dx. Now the fiber over 0 comma 0, the fiber over 0 comma 0 is obtained by imposing x equals to 0 and y equals to 0. Thus pi inverse 0 0, that is v of x comma y in intersection v of xt minus y equals to v of xy x comma y, which is contained in v of xt minus y on the coordinate rings. This fiber is b mod x ideal generated by x comma y isomorphic to ct, and therefore pi inverse 0 0 is isomorphic to spec of ct, which is isomorphic to a1, and as a topological space of complex point, this is homeomorphic to C. And geometrically the fiber is the line 0 0 t, which is isomorphic to C or homeomorphic to C. And note that the image of pi, if we determine this, if x comma y comma t belongs to v of xt minus y and x not equals to 0, then the relation xt equals to y simply says t equals to y mod x. So every point of d of x occurs in the image, and if x equals to 0, then the equation xt equals to y becomes 0 equals to y. Hence the only point of C2 with x equals to 0 that can lie in the image is 0 0. Therefore image of pi equals to dx union 0 0. And for the conclusion, you see that the projection pi of v of xt minus y to C2 is an isomorphism over the open set dx, and the fiber 0 0 is the affine line A1C which is isomorphic to C, and the image is exactly dx union 0 0. Now let us focus on the next problem. Okay, so let us solve the problem. Uh, let A be an integral domain with a spec of A is 0 comma p, and let A be the fraction ring of A, fraction field of A, that is quotient field of A, and set B equals to A mod P cross F, and define a ring homomorphism phi of A to B, is that A going to pi A comma A, where pi A is the residue class of A modulo P, so that the induced map on spectra phi star from spec B to spec A is bijective and not a homomorphism. Now we prove the answer in two parts. First we have to describe what is spec B. But, since P is the unique non-zero prime ideal of A, it is maximal, and hence A mod P is a field, and also F is a field. Therefore B equals to A mod P cross F is a product of two fields. Now for a product of rings R cross S, the prime ideals are exactly those of the form P cross S and R cross Q, where P belongs to spec R and Q belongs to spec S. And since both factors of B are fields, each has only the 0 prime ideal, the spec B has exactly 2 points, n1 equals to 0 cross F and n2 is A mod P cross 0, and so spec B equals to n1 comma n2. Now we compute the induced map phi star. By definition, phi star Q equals to phi inverse Q, and for each Q from belongs to spec B, we compute the two pre-images. The pre-images n1 equals to 0 cross F. We have phi inverse n1 is A of capital S, as that pi A comma A belongs to 0 comma F. This means pi A is 0, and that is for A belongs to P. Hence pi inverse n1 equals to P, and the pre-image of n2 is A mod P cross 0, and we have pi inverse n2 as A of capital S, as that pi A comma A belongs to AP cross 0. This means A equals to 0 in the field F, hence A equals to 0 in A, therefore phi inverse n2 is 0. So the induced map is phi star n1 equals to P, and phi star n2 equals to 0, and since spec A is 0 comma P, this shows that phi star is bijective. Now show that phi star is not a homeomorphism, and we now compare the topologies. Topology on spec A is A has exactly 2 prime ideals, therefore the only open subsets are phi 0 and 0 comma P, and 0 is D of F for any F that belongs to P minus 0, while P is not open, and so spec A is not discrete space, and the singleton P is not open. Then topology on spec B is let E equals to 1 comma 0 on B, then E is an idempotent and D of E is n1, and n1 does not contain E, while n2 equals to A mod P cross 0 does contain E. Thus n1 is open, and similarly n2 is open, hence spec B is discrete 2-point space. Now phi star n1 is P, and since n1 is open in spec B, but its image phi star n1 equals to P is not open in spec B, the inverse map phi star inverse cannot be continuous, therefore phi star is not a homeomorphism, and we conclude that the induced map is bijective, not a homomorphism. Now let us look into the next problem, which says that let K be a field and phi of A mod A prime be a homomorphism of K algebras, and let phi star from spec A prime to spec A be the induced map on spectra. Assume that A prime is of finite type over K, so that the image of every closed point x prime of spec A prime is again a closed point of spec A, is the assumption that A prime is of finite type over K is necessary. So we give the answer in two parts. First one says that the closed points map to closed points when A prime is of finite type over K. Let x prime of x spec A prime be a closed point, then x prime corresponds to a maximal ideal M prime of A prime. We must show that P equals to phi inverse M prime is a maximal ideal of A, and since A prime is of finite type over K, the residue field K of x prime equals to A prime mod M prime is a finitely generated K algebra, which is also a field. By Zariski's lemma, such a field must be a finite field extension of K. Hence Kx prime is a finite dimensional vector space over K. Now consider the composite map A to A prime and to A prime mod M prime equals to Kx prime. Its kernel is exactly P equals to phi inverse M prime, so it induces an injective K algebra homomorphism A mod P to Kx prime. Therefore, A mod P is a k-sub algebra of a finite dimensional k vector space. Hence, it is itself a finite dimensional over k. Now, moreover, A mod P injects into the field kx prime. So, A mod P is an integral domain. A finite dimensional integral domain over a field is a field. And if 0 not equals to A belongs to A mod P, then multiplication by A is an injective k linear map on the finite dimensional k vector space A mod P. Hence, it is surjective. In particular, one lies in the image of multiplication by A, so A is invertible. Thus, A mod P is a field, which means P is a maximal ideal of A, and therefore phi apostrophe x prime equals to P is a closed point of spec A. Now, the finite type assumption is necessary. No, the assumption is not necessary. Is not in general. Here is a counter example. Take A equals to kt and A prime equals to k first bracket t, and let phi equals to A prime be the natural inclusion. Then A prime is not finite type over k, and the spectrum spec A prime consists of a single point, namely 0, and this point is a closed point because A prime is a field. However, phi apostrophe 0 equals to 0 spec kt, but 0 is not a closed point of spec kt, since the closed point of spec kt are precisely the maximal ideals ft with a irreducible in kt. So, without the finite type hypothesis, a closed point of spec a bar need not map to a closed point of spec a. So, therefore, yeah, if A prime is a finite type over k, then phi apostrophe sends closed point to spec a prime to closed point of spec a. Now, let us move on to the last problem. Try this for 5 to 10 minutes, then we will start. Okay, so let us do the last problem of today. Let K be a field and XYT be the indeterminants over K, and consider the K algebra homomorphism phi from KXY, that is K of capital XY by mod ideal generated by capital Y square minus capital X cube to KT, and defined by small x going to T square and small y going to T cube, so that the induced map spec of K capital T going to scape of spec of K of small xy is homomorphism, although phi is injective but not surjective. Now the homomorphism phi is injective but not surjective, because if you consider the composition K of x comma y to kt by x going to T square and y going to T cube, the image satisfies the relation that T cube to whole square equals to 2 to the power 6 and T square T cube T square whole cube. So the kernel contains y square minus x cube. In fact, this is exactly the kernel. We obtain an injective map phi kx comma y to kt. However, phi is not surjective since T does not belong to image of phi, and every element of the image is a polynomial in T square and T cube, hence has only even or at least cubic degrees, but cannot produce T itself. And if you consider the description of the spectra, the spectrum of kt, prime ideals in kt are either 0 or generated by irreducible polynomials. Spectrum of kxy, the ring kx, y isomorphic to kt square t cube belongs to kt is a domain, so 0 is a prime ideal. Other primes correspond to algebraic subsets of the curve y square equals to x cube. If you consider bijectivity of phi upper star, we show that every prime ideal of kx, y is the contraction of a unique prime ideal of k capital T, and let small q belongs to spec of k capital T, then phi upper star q equals to phi inverse q is a prime ideal of kx, y. So phi upper star is well defined, and if you consider injectivity, suppose q1 not equals to q2 in spec of kt, and since kt is a PID, distinct primes correspond to distinct irreducible polynomials, the contraction phi inverse qi remain distinct because phi is injective, thus phi upper star is injective. And if you consider surjectivity, let small p belongs to spec of kxy, and since kxy belongs to kt, we can consider the extension ideal p of kt which belongs to kt. Since kt is integral over kxy, t square the t satisfies the equation t square minus equals to 0 in the fraction field sense, and more concretely kt is integral over k of t square comma t cube lying over the whole therefore there exists a prime q of kt such that q intersection k of x comma y equals to p. Hence phi upper star is surjective, and thus phi upper star is bijective. And local isomorphism on dx, let sx equals to x to the power n greater than equals to 0, the set of all xn, then sx inverse k of xy equals to kx comma y x, and sx inverse kt equals to kt of t square. Since x belongs to t square, localization gives this map, and now in kt mod t square the element t becomes invertible map up to multiplication. Hence kt localized at t square equals to kt localized at t, that is k comma t of t inverse. And similarly in kxyx we see that therefore phi upper star dt square going to dx is a homeomorphism. Now we have to conclude that phi upper star is a homeomorphism. We now use a standard fact that a continuous bijection between spectral spaces is a homeomorphism. If it induces a homeomorphism on the basis of opens. Here phi upper star is bijective. It induces a homeomorphism on the basic open set dx. The complement Vx is a single point, and bijectively ensures a correct behavior there. Hence phi upper star is a homeomorphism, and the map phi upper star spec t to spec of kxy is homeomorphism, even though phi is injective but not surjective. So therefore we are done. So thank you everyone, and good night.